In this video, we're going to look at the acid-base chemistry of some aqueous transition metal ions. And you'll notice that in my lineup, we have some typical transition metal ions, chromium 3+, and iron 3+, copper 2+, iron 2+, and cobalt 2+. We've included aluminium here because it's typical of the chemistry of 3+ ions. Here, Rianne has taken some iron 3 solution, which you can see is orange. What she's now going to do is to use a calibrated pH probe, you can see there it's reading pH 7, and put it into the solution of Fe3+ ions. And surprisingly, the pH now drops to 1.9, so it's about pH 2. Why is that? And if the pH of the iron 3+ solution is about 2, what's the concentration of the hydrogen ions in there? So if pH is minus log of the hydrogen ion concentration, and 10 to the minus pH is equal to the hydrogen ion concentration, the hydrogen ion concentration in this solution is 10 to the minus 2 moles per dm cubed. Where are these hydrogen ions coming from? We decided to test that with another 3+ ion. This time it's aluminium 3+. First of all, on some universal indicator paper, and you can see that the orange colour means it's acidic. So we decided then to take the pH. So we immersed the pH probe in a solution of Al3+ ions, and you can see that the pH dropped to about 3.5. So aluminium ions are also acidic in aqueous solution. To investigate whether this was anything to do with the charge on the ion, we decided to investigate a series of 2+ ions in aqueous solution. Let's look at Fe2+. This is our solution of Fe2+ ions, a characteristic pale green colour. Now, even though this video is a little bit shaky and Rianne was overzealous with the amount of solution, you can see that the pH when we put the probe in goes down to, you can see there, roughly about 6.4. We decided to repeat the experiment with some aqueous cobalt 2+ ions. So there's the characteristic colour of the pink cobalt 2+ ion, and again, taking its pH, we found out that it was ever so slightly acidic at pH 5.7, but nothing like the iron 3 and the aluminium 3. So it was slightly acidic. So we've now seen that solutions of iron 2 are not really noticeably acidic, whereas we saw that iron 3, which has got a pKa of 2.2. Now that pKa is even smaller than ethanoic acid, and ethanoic acid has got a pKa of 4.8, which means that this is a much stronger acid. So we need to ask ourselves, why is this species acidic at all? And why is it much more acidic than iron 2+ ions? Well, we need to look at the central ion here. And it's because that the Fe2+3+ ion is smaller and highly charged. We say it has a higher charge density. And charge density is the charge on the ion divided by the ionic radius. And therefore, the smaller the ionic radius, the larger the charge density ratio. And the larger the charge density ratio, we say the greater the polarizing power of the central metal ion. So that's called the polarizing power. So the impact of that is that the central Fe3+ ion here attracts electrons from the neighbouring water molecules. So if we look at this neighbouring water molecule here, where this is normally slightly negative and the hydrogen is slightly positive, the pull of the electrons towards the pull of the electron pair towards that central highly polarizing Fe3+ ion is to increase the polarization or the dipole on the water molecule, and therefore weakening the OH bond within the water molecule. So this complex ion will readily release H+ ions or protons. So these hydrogen ions, these hydrogen atoms here, are all really weakly held and will readily be released to the surrounding solution. So let's explain that again so you could explain it in an exam situation. The Fe3+ ion has a higher charge density ratio. Therefore, this makes it more strongly polarizing than Fe2+ ions. The ion attracts electrons of the oxygen atoms in the water ligand. This weakens OH bonds in the water molecules. The complex will then readily donate protons, which we know are H+ ions. Now, it's easy to say this in writing, but a picture paints 1,000 words. So always use this illustration to define your point. What we're going to do now is look at the reaction of this acid, because it is a Bronsted-Lowry acid, because it is a proton donor, with a variety of bases. So let's first of all look at when the base is a water molecule. So this is going to release protons, and therefore in aqueous solution is surrounded by many other water molecules. And these water molecules are going to be naturally attracted to this whole complex because of the 3+ charge spread over the whole complex. Now, one of the water molecules would be attracted to one of these weakly held hydrogen atoms on one of the water ligands. And because of the weakening of the bond, this could donate its lone pair of electrons to a hydrogen atom, and this bond will break. Therefore, this is behaving as a Bronsted-Lowry acid, and the water molecule on the outside is behaving as a Bronsted-Lowry base, and that is a proton acceptor. The resulting species is now going to have a 2+ charge because it's lost a proton. And there, the proton has gone here, so this would leave behind a hydroxide ion, which has a negative charge. So the overall charge now is 2-. The H2O water molecule on the outside will now become a H3O+, or hydroxonium ion, or oxonium ion, with a positive charge. And we know that the oxonium ion, or the H3O+ ion, is what is responsible for acidity. Let's write that reaction as a balanced equation, where our water molecule is the base and the hexa-aqua ion 3 is behaving as an acid. The resulting species has lost a proton, and this is what causes the solution to have a lower pH, the presence of the oxonium ion. Now, if we look at the equilibrium for this reaction, we can get a value for the acid dissociation constant, which in the textbook tells us that pK is 10 to the -2. So Ka is equal to 1 times 10 to the -2 moles per dm cubed, which tells us compared to ethanoic acid that this ion tends to release protons much more readily and move in this direction. So let's have a look at different bases other than water molecules. In this experiment, we added some solid sodium carbonate to a range of aqueous metal ions, some 3+ ions, and then compared it to some 2+ ions. So here's the reaction when sodium carbonate was added to aqueous aluminium 3+ ions. You can definitely see a lot of effervescence there. Let's now repeat it with some chromium 3+ ions. So here comes the sodium carbonate, and again lots and lots of effervescence. As the reaction subsides, you can see that there is definitely a precipitate there, green precipitate. Let's have a look with some iron 3 ions. Here comes the sodium carbonate, and again lots and lots of effervescence. As the reaction subsides, we can see there again a orange coloured precipitate. I went on to repeat it with 2+ ions, and copper 2, you can see there hardly gives any effervescence at all. So we repeated that with iron 2, no effervescence and a precipitate, and we did it with cobalt 2 ions as well. You can see there is no effervescence, and when we shake the tube we can see a precipitate appearing. We'll look at the nature of these precipitates later. But the 3+ ions are definitely giving more of a reaction. So let's have a look at that reaction in more detail. Now we know from GCSE chemistry when an acid reacts with a carbonate we get carbon dioxide and water. So for every 2 moles of the oxonium ions we've got 1 mole of carbonate. But what was the nature of that precipitate? Well, if this species here loses 3 hydrogen ions, then the overall complex will have no charge. And when it's got no charge, it can no longer be soluble. And therefore, the nature or the identity of that precipitate that was left behind, as we can see here, the iron 3 reacting with the carbonate, the nature of that precipitate must have been the FeOH3, where it had lost 3 protons. So each of these were lost. So 3 protons were lost. And therefore that leaves us with FeH2O3 OH3 or iron 3 hydroxide. That has now precipitated because it no longer has a charge. And if a complex doesn't have a charge, it means it's not going to be very soluble in water. So let's now balance this equation. We know that the final product, the precipitate, is iron 3 hydroxide, which is a solid, and we know the reactant is our hexaaqua ion. We know that the identity of the gas can only be carbon dioxide, and we know that whenever carbon dioxide is produced, we also get water. Now we also know that every one of these loses 3 protons, and therefore we're going to need at least 3 carbonates to remove those protons, and the carbonate has a 2- charge. So to balance out this charge, 3 times -2 is -6, and therefore we have 2 of these, and 2 times +3 equals +6, and that's the best way of balancing this. Therefore on this side we're going to form 2 moles of the precipitate. Therefore if we've got 3 carbonates we're going to form 3 carbon dioxide, and therefore for every carbonate there is 3 moles of water. And that is the best way of balancing this reaction. And this reaction always forms the precipitate because in this equilibrium here, as a oxonium ion reacts with a carbonate, the equilibrium is driven forward so that one by one a proton is removed. We can't remove any more protons from this neutral complex because carbonate just isn't a strong enough base. So the nature of that precipitate is quite simply iron 3 hydroxide. So are you able to write a balanced equation for the reaction of sodium carbonate with aqueous aluminium 3 ions? Pause the video and try and write out an equation for that reaction. So again, the hydrated aluminium ion has exactly the same number of water molecules. The protons are removed and they react with the carbonate ions. So remember you need 2 of the aqua ions to react with 3 of the carbonates, and therefore you're going to form 2 of these. You're therefore going to form 3 moles of carbon dioxide gas, 3 moles of carbon dioxide gas, and 3 moles of water molecules. As there's no overall charge on the precipitate, you don't really need to put the square brackets around it. You wouldn't get penalised for putting the square brackets around it. Pause the video and write out an equation for the reaction of chromium, hexaaqua chromium ions. with sodium carbonate. So again, in general, when you have an aqueous 3 ion, it would react 2 moles of the 3 ion would react with 3 moles of the carbonate to give 2 moles of the precipitate of the metal 3 ion, 3 moles of carbon dioxide and 3 moles of water. So let's now look again at iron 3 ions, aqueous iron 3 ions reacting with aqueous sodium carbonate. So we can see clearly that when the two are added, you're getting a precipitate and the effervescence that you can see in the tube as the carbon dioxide gas is coming off. Let's see that again with aqueous aluminium ions. A precipitate of aluminium hydroxide and carbon dioxide effervescing off. And finally with aqueous chromium ions, aqueous chromium 3 ions. We can see clearly the precipitate of chromium 3 hydroxide and effervescence as carbon dioxide gas is evolved. Now let's take a look at some of the 2 ions with sodium carbonate. The next one is cobalt 2. This time some sodium carbonate solution is placed into our cobalt, our hexaaqua cobalt, and immediately you can see a pink precipitate, but this time there is no effervescence. This time it's not an acid-base reaction. There is no carbon dioxide and the precipitate is in fact a ionic compound of cobalt carbonate and the 6 water ligands are kicked out. So it's a precipitation reaction and not an acid-base reaction. This was repeated with another 2 ion, iron 2 So remember, our Fe2 aqueous ion is a very pale green. The sodium carbonate solution is now added to our Fe2 ions in aqueous solution. A pale green precipitate forms, but there is no effervescence. Again, a precipitation reaction and not an acid-base reaction has taken place, and 6 water molecules are substituted, but a precipitate of iron 2 carbonate is formed. Let's repeat this with a further 2 ion. This time we're going to use copper 2 ions in aqueous solution. So the characteristic colour of aqueous copper 2 ions is blue, and we're going to add some aqueous sodium carbonate to them. So once again, you can see a blue precipitate is formed, but there is no evidence of effervescence. Again, the 2 ion has not behaved as an acid. Instead, we have a precipitate of copper 2 carbonate and the 6 water ligands are replaced. So let's do a quick comparison of the 3 ions versus the 2 ions. So the 3 ions that we looked at were aluminium, chromium and iron. And the 2 ions that we looked at were iron 2, cobalt 2 and copper 2. It helps if you remember the colours. Fe3 rusty, Fe2 R2 snotty green, cobalt 2 is lovely beautiful pink colour, and copper, think of copper sulphate blue. Chromium orange to green, you go into jail. Chromium 3, the reduced form of chromium, and as we know, aluminium is not a transition metal, so its solutions are going to be colourless. So all of the 3 ions we say are more acidic, and remember that was due to the charge size ratio, which makes them more polarizing we saw that the pH was lower. The pH was roughly about 2 to 3, whereas the 2 ions are much less acidic and therefore they're not polarizing, so their pHs are roughly around 5 to 7. And the biggest teller was the reaction with the carbonate. So remember that for every 2 moles of the aqueous metal 3 ion reacts with 3 moles of the aqueous carbonate ion. That then results in a precipitate of the metal 3 hydroxide, and it's a hydrated metal 3 hydroxide, and there's no charge on it, and it's not polar because there's no charge, and therefore it precipitates out because water molecules are not attracted to it. You also get 3 carbon dioxides and 3 waters. The reactions of the 2+ are not acidic at all, and all that happens is the metal 2 carbonate reacts with the carbonate ion, and you simply get a precipitation reaction where you form 1 mole of the metal carbonate, which precipitates because it's insoluble, and the 6 water molecules are then kicked out. In this final part of the video, you're going to be shown some reactions, and what you're then going to be asked to do is to write a balanced equation for the observation. The answers will appear later on, but it'll be good to test your knowledge. Write a balanced equation for the reaction that's taking place in this video here. Pause the video and then check your answer. Pause the video now. Did you get this right? The blue species is the aqueous copper ion, and 2 hydroxide ions behaved as bases. The precipitate had to be copper 2 hydroxide because it's completely lost its charge and therefore it precipitates, and 2 protons have been removed, so we form 2 moles of water. This time we've got aqueous cobalt 2+ ions and sodium hydroxide solution. What do you observe, and can you write a balanced equation for that reaction? Your observation is the pink solution, because it's transparent, you can see through it, gives a blue precipitate. You don't need to elaborate on the colour blue. You could have said a purpley blue, but blue will do. The equation for the reaction is the formula of the aqueous cobalt ion. The hydroxide ions are behaving as a base. This releases 2 protons to the base that forms 2 water molecules, so therefore the species that has lost 2 protons has got no charge, and therefore it's no longer soluble in water. So here is sodium hydroxide and aqueous ion 2 solution. What do you observe? And could you write an equation for the reaction? And also, could you explain why it starts to go orange around the top after the solution, after the precipitate has been left to stand in the air? So observations and an equation for the reaction and an explanation as to why it's going orange around the top. Pause the video now and then check your answer. So for your observation, did you say that the pale green solution gave a pale green precipitate? And then did you say on standing you got this orange brown colour at the top? So initially it's simply an acid base reaction where the protons from the hexa aqua ion 2 are donated to 2 hydroxide ions, and therefore they're behaving as a base. They take off the protons and form water, and to cancel out the charge, it's lost 2 protons, it's got no overall charge, and therefore it precipitates out. So the green precipitate is iron 2 hydroxide. Now on standing in air, iron 2 hydroxide isn't stable, and it rapidly oxidizes to iron 3 hydroxide, so it loses yet another proton and becomes oxidized to iron 3 hydroxide. So that's oxidation in the air. So an explanation for that oxidation is in the Fe2 ion there is a pair of 3d electrons repelling, and the repulsion is minimized when it loses yet another electron, and this tends to happen when iron is in alkaline solutions. we have iron 3 in aqueous solution, iron 3 ions, and some sodium hydroxide. What's your observation and what's your equation for the reaction? Pause the video now. So was your observation that the orange or orange-brown solution gives an orange or orange-brown or rust precipitate? This time, because the iron has a 3+ charge, it's able to lose 3 protons, and therefore we need 3 bases. So 3 hydroxide ions remove 3 protons. The precipitate is iron 3 hydroxide, and 3 protons removed, so the 3 hydroxides become 3 water molecules. When chromium is reacted with sodium hydroxide, watch carefully what happens when the test tube is shaken and an excess of sodium hydroxide is added. So there's the initial sodium hydroxide, and I'm now going to add the sodium hydroxide in excess. And this didn't happen with any of the 2+ or the 3+ ions. So let's have a look what happens when we add the sodium hydroxide in excess. Can you write an observation for that reaction? And can you write equations for the reaction that took place? Pause the video now. So your observation, a green solution gave a green precipitate, which then redissolves in excess sodium hydroxide to give a green solution. Let's write 2 equations for that. Pause the video if you think you can do it, and then check your answer. So in the precipitation reaction, 3 hydroxide ions remove 3 protons to form chromium 3 hydroxide. It precipitates out because it's got no charge. It then redissolves because the chromium ion is so polarizing. This can further behave as an acid and lose yet another proton to another hydroxide ion, and now it's recharged. So now we have lost yet another proton, so we now have only 2 waters. We now have 4 hydroxide ions. The overall charge is now minus, and therefore it redissolves again because it's charged. This also happens with aluminium, as you can see in the next video. So first of all, we can see there a precipitate, and then let's see what happens when that's shaken with excess sodium hydroxide. Here it is again. There's the sodium hydroxide, and now let's add sodium hydroxide in excess. Can you write the observation and equations for your observations? So was your observation that the colourless solution gave a white precipitate, which then redissolves in excess sodium hydroxide to give a colourless solution? Let's now write equations for those reactions. Write it down, pause the video, check your answer. So the first equation, which gave the precipitate of aluminium hydroxide, is a simple acid-base reaction. But then, because the aluminium ion is so polarizing, the aluminium hydroxide then behaves as an acid, and it loses yet another proton from one of these waters, which becomes then AlOH. So H2O, one's been lost, so it's H2O2, and now we've got 4 hydroxide ions, and because it now has a negative charge, it will redissolve again, and that reacted with 1 more hydroxide ion. So the hydroxide behaves as an acid and can lose yet another proton. And that's the end.